So
Yeah,
let us welcome our next speaker, Dr. S.P. Arun. Dr. S.P. Arun received his B.Tech from IIT Bombay and MS and PhD from Johns Hopkins University, all in electrical engineering. After his postdoctoral research at Carnegie Mellon University, he joined the Center of Neuroscience at IISc Bangalore. He is fascinated by how the brain transforms sensory inputs into perception. Over to you, sir.
Can you hear me?
Yes, sir.
yeah.
Yeah, great. So thanks everyone. Sounds like an interesting meeting. I heard a bit of the previous talk as well. I guess it's thematically related what I'll talk about, because I'm also going to be talking about some bit of AI. So let me start sharing my screen and then you can take a look. Okay, great. So can you see my screen?
Yes, sir.
Okay, great. Okay, so this is what I've given as the title of my talk. So just to give you a sense of why I'm saying that this is an interesting problem, I think all of you would have seen images of this kind on the internet, where you're asked to authenticate yourself as a human being, and these are called CAPTCHAs. And just to authenticate yourself as a human being, all you have to do is to just recognize these letters, right? So what's really amazing is that these are actually tests which computers are failing today. And so this is quite remarkable, right? So we have computers that can calculate the square root of 2 to like 30 decimal places, but they can't do something as simple as C. So the question is, why is it that they can't do it? Okay, and this is actually a problem that people, even in the earliest days of AI, were trying to think about, because they quickly discovered that if you want to have a machine that wants to sort of recognize whatever we look at, then it's not easy, because you, even for simple tests like this, they're failing. So what is the problem here? Well, so just to again put a more tongue-in-cheek kind of summary here. So if you think about the hard problems of AI, right? So this is credit to Douglas Hofstadter, who has really nice books on AI and the history of AI as well. So he says, well, one problem is, what is A? Okay, and that's the problem I'll be talking about. You might hold your horses and let me just describe what the problem is. The second problem is, of course, what is I? So I is, of course, intelligence there. And this we won't talk about, because lots of people talk about intelligence. But this first problem is sort of interesting, right? So let me give you a sense of what what I'm really talking about. Here is a bunch of different here's a bunch of different renderings of A, and you can see here that all of these things actually you're easily and readily able to recognize as a letter A. But then all of them have very different properties. They look very different, but still we know that these all look like A. So the question is, what is A? And somehow we all understand the idea of A-ness. Right, so this is quite a fascinating, sort of idea if you think about it, because despite so many variations in form, we're still able to recognize that letter A. Okay, so that's why I said, what is A? And more broadly speaking, there's this paradox called Moravec paradox, named after the person who talked about it. And basically he says, whatever we find hard is going to be easy for computers. So if you want to multiply, 2465 into 5566, that's easy for a computer. But what we find really easy is actually going to be hard for computers. And this is exactly exemplified by what I talked about, which is the act of seeing. Just by looking around, we know what is where in the world. And that's actually really easy. That's an easy thing for us, but very hard for computers. Okay, so some of you might be thinking, well, what about AI and deep networks? And there's remarkable sort of advances that are being demonstrated today. So vision, speech, computers are solving chess. They're also playing the game of Go. And if you believe all the media hype, it looks like really AI is going to solve all the major problems of the world. Global warming, world peace, bring about all that. But the problem is that currently AI is actually not performing even on vision the same as we do. Okay, and this just to give you an example of in a real world problem, just to find people in an image, right? And this is pretty important task in the case of driverless cars and things like that. The state of the art AI is still doing only 80%. That means every 10 images, it's only getting 8 right, whereas humans are actually almost always right. These 96% performance is actually on a speeded task where sometimes they make errors, because of just being primed by the previous trial or something. But humans are actually almost 100% on these tasks. Okay, so still there's a bit of a performance gap. And plus, there's a bigger problem also, which you might have heard about in maybe other talks as well. And this is the problem of adversarial images. So here's an example image. The computer will successfully call this a panda, and it gives you a certain confidence rating with it. But you add a very, very small amount of noise, and now the computer is actually going to call this a gibbon, which is a completely wrong answer. Okay, and this kind of examples have been found for deep neural networks, which have been trained for object recognition. So they're actually optimized on a bunch of data sets, but still there's some weird problems with them. And this is even worse if you take these abstract patterns where the computer is calling this pattern a penguin and this pattern a starfish, and we have no idea why they're calling it like that. So there's something fundamentally different about how we see versus how we are able to make computers see. And that's really what I'll try to talk to you about today. So here's the question. So how is the brain solving vision? Okay. And here's a diagram of the monkey brain, just to give you a sense of it. And our brains are also very similar. The eyes are in the front of the head. The information goes from the eyes to the back of the head, where there's a primary visual cortex. And what's shown here in the diagram is actually all the regions in the brain which are involved in processing visual information. Okay, so you can see that actually quite a large part of the brain is dedicated to vision. And so think about it, right? You have a very small piece of tissue in your retina. It's sensing the images that you're looking at. And then a huge part of your brain is actually dedicated to that part of that small piece of tissue. Okay, and that actually highlights two things. One is vision is a very important sense for us. It enables us to see very, very far away, much further away than hearing and of course touch. And of course, all the other problem, the other thing that it also tells us is that vision is a very hard computational problem. Computers actually, just like computers find vision very hard, even our brain is actually finding vision very, very hard. And therefore, it's spending a lot of brain real estate in trying to solve the problem. Okay, so this is an overview of our lab. This is this vision lab at ISC, and basically the question that we are trying to investigate is how the brain solves vision. And we have 4 different ways of answering this question. The first way is to understand visual perception in humans. The other way is to actually look inside the brain a little bit. We're using all these techniques called fMRI and TMS, and these are ways to image the brain and look at it at a very coarse level, and of course also perturb it using magnetic pulses. The other thing that we also do is to record from single neurons in the brain of animals, and finally, of course, we also use computational modeling to figure out what is going on. So let me show you. Let me start by again getting back to this original question of how is object recognition, or how do we recognize objects in a computer and in the human brain. Okay, so here's an image that we might look at. All of you know this person. In a computer, you would actually extract some features that are unique to this person. So there's some image features that are extracted, and then that is sent to a classifier which takes all the features. And one of the problems is, of course, that the image will change. And so the same image of Tendulkar from a different viewpoint or a different lighting condition will change the image. So you want to extract features or properties of the image in such a way that the image actually, although the image of that person is changing, you want to extract sort of stable features. And these features are fed to something called a classifier. And then finally, you're able to recognize this person and say, okay, that's a person. Okay. Now, in the human brain, a very similar sort of stage happens, a similar sort of processing happens. Here's another image. And now the image extraction or feature extraction is happening in the visual cortex, like I showed you. And we know from many decades of neuroscience that there's lots of complex feature processing that's going on. Then the feature processing, the output of all that feature processing is going to a region called the frontal cortex. And that's the prefrontal cortex over here. And some decisions are being taken about the image. And so by looking at this person, you of course all recognize this person, and the frontal cortex sort of makes some sort of decision about it, some decision about who the person is. And here you of course classify this here as God. And I said it, Dhoni is God and Tendulkar is. And so if you now want to compare machines and humans, and you want to understand why is it that machines are actually performing worse than people, then how do we understand? Well, very obvious thing is to compare performance, right? So you can say, okay, I want to compare machines and humans on the same task. So how do I go about comparing? Well, that's exactly what we decided to do. We'll just compare the performance, okay? But there's a big difference here. If you take a very, very easy task, then humans and machines are both going to ace the task. And then you won't know why they're behaving differently, because actually the difference is actually coming on a hard task. So what we want to do is to sort of differentiate between people and machines. You want to actually make them both perform a very difficult task. Okay, so that's exactly what we decided to do. This is Harish in our lab, who is a postdoc and now a scientist at NIH. And the question that we decided to ask is something actually very familiar to all of us. Okay, this is a problem of we every day, almost every day we have this experience of looking at people in India, and very often you can tell where they're from. So here's just a caricature of, like, we took this is what we did in our study. We said that anyone who's actually from the northern part of India is this is what we defined as North India, and then we took the southern part of India, people coming from these states as southern part. Okay, so now we said, well, we all have this everyday experience that you look at a face and you can say, oh, he's from North India, he's from West Bengal, he's from Kerala, and so on. So question is, what features are you using? How do you tell that somebody is from North India or South India, or he looks American, or he looks Chinese, and so on? Okay, so that's the question we wanted to investigate. So we collected a bunch of photographs from people. So these are all the photographs that we collected, and we asked them, where are you from? Where are your parents from? And we made sure that they're actually from the geographical north or geographical south of India. Okay, and so here's the performance actually. Here are North Indian faces. And what was very interesting for us is that there's actually a wide range of variation. So some people are actually misclassified. So every time people saw these images, they thought that they were South Indian. But in fact, these people were North Indian. We asked them. Okay. Similarly, there's a lot of faces that people very systematically across, this is 83% of our subjects called this particular face as North Indian. 89% call this particular face as South Indian. So clearly people can do the task. But also there are a bunch of hard faces where people are not very accurate. Okay. They're not able to tell who's from North, who's from South. So, and same thing for South Indian faces. Okay, and I think all of you might appreciate that you're also having the same experience, that some faces are looking like from a different region in India, and some other faces are looking from a different region. Okay, feel free to ask if you have questions even now, but I'll just keep going if you don't ask. If you're not asking anything, then assuming that you understand what's going on.
Arun, one obvious question that will arise here is, how do you define a North Indian? I mean, have they just moved from south to north recently? Or
right. So in our case, we just correct. So we just defined it as biologically, as in like the parents are from northern part of India. So if both the parents are from north, then we assume that we define them as from north of India.
So first generation North Indian.
So essentially, we assume that if you're North Indian and you come to South and start eating curd rice and idlis, your face won't change.
Right.
Okay. And I think that's a fair assumption to make, although maybe something happens to your face if you're doing these things. Yeah. So that was just an operational definition, and we also excluded states which either were in between or didn't also had very clear stereotypes. So then that's a subcategory and so on. So that was just an operational definition. Not making any statements about North and South as categories. Yeah. So now what we wanted to know is, can we train a computer to do the same exact task? And you can see that the task overall is actually not easy for people. And there are phases where the person is from north or south, and even people find it hard to actually classify it. So this is a hard task, and so we said, okay, how do computers do this? So how do you do this in a computer? Well, there are two ways of doing it. All of you must have heard of deep networks in one way or the other, even during this meeting and before. And so in the deep neural network, what happens is you take a face and then it's processed by a bunch of layers. And these layers are extracting various kinds of features from the image. And then there's a whole series of processing, at the end of which you'll get some nice feature set. And the idea is that if you have a nice feature set, you can classify what that face is. And you can say whether it's from north or south. Now, the other way is that you use manual features. And the reason for doing that is because if you take the deep features, you don't know which part of the face that you're actually using for recognition. Whereas in manual features, I can go back into the classifier and say, okay, which part of the face was it actually using? So this is what we did. So every face was registered to some automatic landmarks. This is done with the computer. Computers, by the way, do this pretty well. And maybe they do it even better than humans, or at least as good as humans. So they do it pretty well on this. Then we also extracted intensities, just the brightness of different parts of the face. We also extracted various measurements of different parts of the face. And basically, now you have different sets of features that you can feed into the computer and say, use this for classification, use that for classification. Okay. So here are the results. Many models showed comparable accuracy to humans. So this is what's shown over here is human accuracy. So humans are about 64% correct. Not a great exam score to have, because it's a hard task. Okay. Now, if you take the best performance of a computer, it's actually 61%. So computer is also doing pretty well, right? I mean, if two students took an exam and one got 64 and the other got 61, you won't be particularly upset, or you won't say that these two are too different. And in fact, there's some algorithms that actually even do 63% and so on. The reason I highlighted this one is actually this is a deep neural network, and this is actually a case where regular computer vision algorithm was actually able to do better than a deep network. So that was kind of interesting. But now you can say these two performances are there. Humans are also doing 64% on the task. So some faces they're getting wrong. And the computers are also doing 60% on the task, and they're also getting some faces wrong. Now the question is, do the faces that are mistakenly classified by humans, are they also mistakenly classified by computers? Okay, are they making the same mistakes, right? So, and there's the famous thing like know the mistakes and know the man and so on, right? So like in this case, we are looking for what are the mistakes that humans are making, and are they the same as what computers are making? And so what I'm plotting here is the correlation with human errors. So human accuracy on faces, and what's on the x-axis is basically different computer vision algorithms. So all kinds of feature sets and so on. I'll explain those in a little bit detail later. But this bar on the right-hand side actually is the consistency of human subjects with each other. So in other words, if you made a mistake on a particular set of faces, and I look at my pattern of mistakes, two humans actually are very, very consistent on the pattern of mistakes they make. So basically, despite the fact that you might have seen a totally different set of faces growing up and in your visual experience, or I might have seen a different set of faces, we all have reached the same type of mistakes. But the computers are actually making a very different pattern of mistakes. You can see this is the match between computers and humans, and computers are making totally different set of mistakes. And even if you train these algorithms to actually predict human accuracy and not really actually classify faces as north and south, still we see a very systematic gap between computers and humans. So there's some very systematic difference between the way computers are processing images or seeing images compared to the way that we are doing it. Okay. So that's what we have there. So you compare machines and humans on hard tasks, and this reveals actually systematic differences in their error patterns. So that means there's something fundamentally different about what we see and what computers are seeing. So then the question is, well, can we go beyond comparing performance? And this is actually a study that Pramod did in our lab. He was a PhD student and he's now a postdoc out in MIT. And so we came back to this original thing that we showed, and we said, well, you can compare performance, of course, but then you're looking at the output of two complex decisions. One is to extract features. The other is to actually make a decision about the face. So the question is, can I somehow compare the features in some sense? Okay, can I understand the properties that humans are extracting from the image, and can I understand the properties that computers are extracting from the image? Okay, so then how do we even do that? Well, in a neural network, there are lots of units. And in the brain also, there's lots of neurons. So I don't know whether the first neuron here matches the second neuron there and so on. It's not really something that I want to compare. And I can't anyway get a direct correspondence one-to-one, because you can have two feature sets which are different from each other, but they're really just rotations of each other. So what we really want to do is, if you have images arranged in some space, what we really want to do is not to compare features, but rather to compare distances. So what I mean is, whether the neural network has more units or the brain has more units, we don't care. All we want to know is whether things that look different to us also look different to humans, also look different to computers. Okay, so that's the question that we want to ask. So then the question is, how do we actually understand similarity? Okay, so that is, I want to understand whether two things are similar or dissimilar. How do we do that? Well, first of all, you can't just ask people and say, okay, is the cow different from a fish or is the cow different from a goat? Because they'll just give you a similar answer to both these cases. And we decided to settle on a particular kind of task, which enables us to actually understand similarity. So here's an example. There's an image that I'm showing out here, and there's a leopard hidden in the image. And I guess, I don't know if there's a raise your hand feature over here, but tell me if you find the leopard, okay? Or if you raise your hand, I'll see if I can find it. Find your hand, but raise your hand if you see a leopard. Okay, so it's actually hard to find. Well, why is it that it's hard to find? Well, for those of you who are starting to see it, and I'll just jump into the answer there. Words to see. Well, the answer here is that the leopard is somehow evolved to become similar to its surroundings. So if it's placed in the correct surrounding, it's very hard to find the leopard. Whereas if you place the leopard in a very, if you put it in the middle of the road, of course you can find it, right? So that's a clue for us to actually understand how to measure similarity. And so we can go from very difficult, complex kind of scenes like this to a much more simpler case where I say, I put an array of identical items. I'm sorry, I don't have an example of it. So I put an array of identical items, and then if one item is different from the others and you can find it very easily, then those two items are very different. And if the item is very hard to find, then it's actually very similar. So that's what we do here. So we measure perceptual distances in humans, and it's measured as the reciprocal of reaction time in a visual search task. Okay, and these are all the images that we saw. So what we did now is to make a very elaborate study and show pairs of images, measure similarity using this way, and now I have a bank of similarities to compare computers to. And so how do you measure distances in computers? Well, it's simply the Euclidean distance between the two feature vectors activated by the image. And so you can calculate feature distances using many different popular models. We use a whole range of computer vision models. And the question is, how do computers see an image and how do humans see an image? And so here's the best prediction. On the y-axis, I'm plotting the distances or perceived distances between pairs of images. So for example, these two images look very, very dissimilar to us. These two images look very similar to us, and so on. So there's a whole range, okay? And what is on the x-axis is the best prediction of computational models. And so what you can see that there's actually a pretty wide range. And what we were interested in seeing is cases where the perceived distances between images is much overestimated by the model and underestimated by the model. So here are the pairs which are actually overestimated, which means that the observed distance is much smaller than the predicted distance. That means these images are actually very similar for us, but they're very different for computers. Okay, so you can see here there's a couple of similar properties over here. So you can see that objects that share features are looking similar to us, but for computers they don't look very similar. Okay, now again you can see underestimated pairs where you can see that distances between these objects actually look much more distinct to us compared to computers. Okay, and this in this particular case, it's a symmetry feature. So what we found is that symmetric objects are actually much more distinctive for us, but they're not as distinct for computers. Okay, so that's another interesting property. But the other part was all models actually showed systematic differences. What that means is there are many different types of computational features, many different types of computer vision models. All of these models seem to have the same systematic bias. So if one model shows a bias, all models are showing a bias. And so that's also very interesting, right? So what that's showing us, what it's actually telling us is that humans are consistent with humans, computers are consistent with computers, but they're not consistent with each other. Okay, so there's something special that we are doing that computers are not doing. All right, so that's out here. So then comparing representations in machines and humans actually can reveal systematic biases like symmetry. And I have a few minutes left, so I'll probably tell you a little bit more to say that, well, so far we've been looking at quantitative differences between machines and humans. So the question is, can we look at something qualitative? And this is actually the next study that we did. This is done by Georgian, Harish, and Pramod in our lab. And what we wanted to do was to actually identify qualitative versus quantitative difference. So what do we mean by qualitative difference? Okay, so here's a very famous illusion. Here you can see two faces, and this face is actually made by inverting the features of this face. So this is the face of the British Prime Minister Margaret Thatcher. And the illusion is called the Thatcher Effect after her. And what is interesting about the illusion is here these two faces look very different to us, But if you invert them, these two faces actually look very, very similar. Okay, so what that means is in our perception, these two faces are very different and these two faces are very similar. And so what we realize is that if you think about this illusion, then it tells us something, that the perception is organized in some particular way. It tells us that two upright faces are actually much more perceptually dissimilar than two inverted faces. And so now we can ask the same question in a computer vision algorithm. You can say, do deep networks actually show this Thatcher effect? And what we can do to measure the Thatcher effect is simply calculate an index like this. So you measure the distance between upright faces, measure the distance between inverted faces. If one is greater than the other, then it means that the deep network is also showing a Thatcher effect. Okay, and so that's what we did. So this is the Thatcher index, as we call it, as a function of the layers of the deep network. And so this is what we see across layers. If you take a neural network trained for object recognition, you don't see the Thatcher effect in the final layers. Okay, what that means is that that particular deep network doesn't actually discriminate between upright faces or inverted faces. On the other hand, if you take a network trained on faces, then this is what you get. So this is the neural network trained on faces, and when it's trained on faces, it's actually showing the Thatcher effect. So that's all quite sensible, because the neural network is also trained on upright faces and it's never been shown inverted faces. So obviously it seems to discriminate well between the two. And so this is interesting. But the question is, are there properties which neural networks or computers don't show? And so here's one example of a property that they don't show. All right. So here's an image, and this is, we readily see this as a circle made of squares. And if you do a careful experiment, what you find is that humans can see the circle faster than they see the square. Okay, so in other words, you see the forest faster than you see the trees. So that's sort of the common, simpler explanation of this. So here's the exact measurement that you can make to that corresponds to this effect. So what we said is, maybe the distance between two shapes, which actually, so here's a circle made of squares, and this is a square made of squares. So we'll notice that the components are the same between the two, but perceptually these are very different for us. On the other hand, if you take a circle made of squares and a circle made of circles, then these two are actually very similar for us. So what we said is, the equivalent of this particular illusion or this particular kind of effect is that global changes are actually easy to perceive, but local changes are actually harder for us to perceive. Okay, so this is the question is, then do neural networks or computers actually show this effect? So again, we have the basic effect. The global change is bigger than local change, and the global advantage we can calculate by measuring these distances, and we can ask, do computers actually show this particular effect? And turns out that actually computers don't show the effect. So if you look at this gray bar, this is what human perception is. And if you look at the final layers of this convolutional network, what you see is a local advantage. Okay, so this local advantage actually is what neural networks are actually showing. So this is exactly the opposite of what humans are showing. All right. So we did this for a number of different properties, and this is the list of all the properties where sometimes the computer is showing the effect, sometimes the computer is not showing the effect. All right, so I'll sort of wrap up here. So if you compare machine and human perception, this can actually reveal qualitative differences as well. And I just want to stop and thank all the people in our lab who's doing all this interesting work. And of course, if you're interested in vision research, please do get in touch. And these are all the funding agencies that are actually funding this work. So I'll stop here and maybe take a few questions. Thanks.
Thanks a lot, Arun. Any questions from the participants?
Yeah.
So just the previous slide which you were explaining, can you make it a little more clear to me? I have a few doubts.
Which one?
So what is exactly global advantage, and why is it going down in the?
So we actually did this experiment in the lab. So what we did was we showed, you can imagine an experiment where you show this image embedded in a field of these images. Okay, lots of copies of these, and what it turns out is that people can actually detect this difference much faster than this difference. Okay, so that's the global advantage of it. That is, you're very sensitive to global changes in shape, but you're not sensitive to local changes in shape.
Why does it go down in the final slice?
Yeah. So okay, so all we did was to take a neural network that is actually trained for object recognition. This is actually a VGG16 architecture and it's trained on a bunch of natural images to recognize the objects present in images. And all we did was this analysis where we gave these kinds of images, the circle made of circles, square made of squares and all that. And we asked simply whether the neural network is sensitive to global changes better than it's sensitive to local changes, just like humans are. And it turns out that in the final layers, it looks like the neural network is sort of, deciding on, to focus on local features. And I'm not quite sure why. I don't have an answer because I don't understand how these deep networks actually work. And I think in the field as well, a lot of people don't really understand how they're working and why is it that they're so successful. I mean, they are successful compared to the traditional vision algorithms, but still there's something missing and humans are actually doing something different from what deep networks are doing.
So do we know the biological reason for this difference between the way the machines and the human brain is working?
Biologically, in visual perception, it is known that people recognize objects using the overall shape of the object, and we don't. So, and in fact, when people get damage in their brain because of strokes, you can actually have something called, you can get a condition called visual agnosia. And when people have this kind of condition, they will recognize a pig. And if you ask them, why is it a pig? They'll say, oh, the tail is curly, so it's a pig. They won't say they won't talk about all the attributes of the object as a whole. And so we seem to have this holistic kind of perception. And that seems to be why we have a global advantage.
But even in visual cortex, we have these multiple layers wherein the lower layer captures the fundamental lines, edges, and all. Then complex features go higher level. Isn't that quite similar to the deep network? And where do you find
it is similar at some level, but unfortunately the deep networks, either because of training, actually we have done this analysis on random deep. So if you take a deep network with randomly initialized weights, it shows a global advantage. Okay, so there is a global advantage to start with, but somehow because of the training or because of whatever, you're getting a local advantage after training.
Yes, thank you, sir. Interesting story.
Yeah, thanks.
Am I audible?
Yeah.